Okay, hi. So in the last video, we have discussed about the RAM model. And so we also had an introduction about the best case, the average case, or the worst case. So the best case is the optimistic na view, or this receives the best input, which will give us a minimum time. So this is often trivial or meaningless. The average receives the average input and it also gives us the average time. It will be interesting, but it is actually hard to define what an average case indeed is. While the worst case na analysis, this always assumes that the algorithm receives the worst type of input. And this is the most common way of analyzing algorithms. Okay, and this is the best way to assess whether an algorithm is indeed efficient. All right. So to wrap it up, the analysis on the RAM model can also depend on the structure of the input itself, not the pseudocode, but of the input. Okay. And by considering only the worst possible na inputs, we can remove other dependencies or factors. Okay, now, even talking about the worst case na running time can be a little bit tricky if we want to be really precise. Okay, and as you have noticed from what we have done from the last video, we try to count every single step that the algorithm makes. Okay, so we need to have some kind of way to ignore other details and focus only the most important part. Okay, and we are going to do that using the big O na notation. So we are done discussing the RAM model as well as the worst case running time. Now, from that, let's focus on the big O notation, which is ignoring unnecessary details. Again, what's the motivation? Because it is annoying to count every single step every algorithm makes, and we have to focus only the important part. Now, let's say you have this running time, 2n squared plus 23, or 2n squared plus 27. What does it mean if we have n squared? Or if we have a quadratic na running time? So it essentially means that in a programming standpoint, if we have a nested na loop, right? Okay, so which one is would give us a faster na running time? So it's already here. Both of this will essentially have the same running time. So what about this one? The algorithm A has a running time of 3n squared minus n plus 10. And the algorithm B has a running time of 2 raised to n minus 50n plus 256. Look at both. If you replace the input n with a really large value, that means you have a really large input size, which one would give us a better na running time? So the larger the running time is, meaning the less efficient it is. So, well, the algorithm A, it would be for general cases, but for small inputs, algorithm A and B algorithm B might actually be equal to A or better. So let us see here an example. So let's say the input size n is equal to 5. So that means for algorithm A, the running time will be 80. So essentially what we did here is we replace n with 5. So that will be 3 times 5 squared minus 5 plus 10. So that is 80. But for algorithm B, that will be 2 raised to 5 minus 50 times 5 plus 256. So you can see that the algorithm A is actually more running time rather compared to B. But consider if we increase the input size already. Consider if we increase the input size, assuming that the n is equal to 100. So you can think of it like if you have an array And if n is equal to 5, that means your array has only 5 elements. But if n is equal to 100, that means you have an array with around 100 elements. So if you have an input size n equals 100, your A will have a running time of 29, or algorithm A, which has a quadratic na form, 29,910. But if for 2 raised to n, that will give you this much. Wow. So can you see? Can you see that for small inputs, the algorithm B might be better. But if you increase the input size, you can see how the quadratic is so much more efficient compared to algorithm B, which has an exponential na running time. Okay? So, I joke lang. So, So in big O notation, what we want to do is to remove an important thing. So why do we have to do that? Because if we look at here, if we go back here, 2n squared plus 23 and 2n squared plus 27, basically, they almost have the same running time, only difference with this constant. Okay? And then here, we are more concerned with, we know that 3n squared will have better na running time compared to 2 raised to n. So even if both of them have minus n plus 10, or here minus 50n plus 256, okay? So even if you put here 3n squared minus 500n plus 10, and then this one is 2n minus 50n plus 256, still, this exponential will give you a bigger na running time if the input size is very large. Okay, so what we are going to do is we are going to remove unimportant na things. So we are going to remove this lower order na mga terms, let's say the minus n, and then we are going to remove the constants. So we are left only with n squared and 2 raised to n. So we can then say that this running time of algorithm A is n squared, and for algorithm B, it's 2 raised to n. Okay, so importance is that it allows us to concentrate on the fastest growing part of the function and leave out only the involved na constant. So now that we know which part of the function is giving us that much of a running time, we can focus on improving that part. Okay, so we know that, let's say we know now that this 3 loops is giving us really long na running time compared to having like 1 loop only. So what can we do? What can we possibly do to improve that? Okay, now that is the big O notation. So the big O notation is used to measure how well a computer algorithm scales as the amount of data involved increases. So how well will it work using a 10 element array versus a 10,000 element array? So, so it is not really a measure of speed, but measure how well an algorithm will scale or will grow with input size. Okay? So, and in big O notation, we are essentially going to ignore those unimportant na details, and we will only focus on the most important na part. So we are simply going to look at which part of the function grows the fastest. And we did that by removing the constant, removing the lower order na parts. Okay? So it is a convenient way of describing the growth of the function while ignoring the distracting and unnecessary na details. So again, going back here, so for example, we have algorithm A, which has a running time f of n equals 3n squared minus n plus 10. And then algorithm B with a running time g of n equals 2 raised to n minus 50n plus 256. So we have this big O notation formal definition. We have a function f such that f is a non-negative function such that for every constant C and initial input n sub 0 is greater than 0 such that the function f of n is less than or equal the cg of n for n greater than or equal the initial input n sub 0. Or so we can then say that f of n will be a subset of O of G of n. Okay? So, sinasabi lang dito, titingnan nyo lang, meron lang tayong function f of n, so that will refer to our running time. And then we have some function g of n here with a constant c. And then, sa kahit anong input size na it could be greater than or equal the initial input size. So, more or less 0 ito siya. So, if this is true, if your f of n is less than or equal cg of n. So for example, itong f of n, we know that it is less than or equal to this g of n, right? So we can then say that this function f of n is in O of g of n, or the big O of g of n. So we have here some graph. Okay, so assuming that this is the function f of n, okay, and then we have this function h of n, and this is the function g of n, the red one. So the x-axis is the n, and you can see that uh, the n is growing bigger, or this is the input size, and the y-axis, that will be your running time. So you can see essentially what these graphs are showing are that the growth rates of a certain function, or the running time of each na function, as we increase the input size. So we can see that this is how for f of n, this is the trend of the running time as we increase the input size. This is the trend of h of n as we increase the input size. So which one do you think is better? Which one do you think is better? So it would be f of n, right? Because as you can see, even if we increase the n more, it it essentially just remains constant. Pero yung h of n at saka yung g of n, they constantly grow bigger, or yung running time nila lumalaki. Okay? So which one of the following is true then? Is f of n in O of g of n? So look at this. Look at this one. Is f of n in O of g of n? So yung f of n is less than O of g of n. So yes, it is true. So f of n is in O of h of n. Is it? F of n is in O of h of n. So sinasabi lang yan, na totoo ba na yung h of n is greater than f of n? Totoo ba? So yes, it is. So as you can see, yung running time sa h of n, mas tumataas siya, mas lumalaki as the n is growing compared to f of n. Is g of n in O of f of n? So tingnan natin si g of n at saka si f of n. So pag lumalaki si input size mo, mas maliit ba yung running time for g of n compared to f of n? No, it is not. Okay, that's why hindi siya totoo. But g of n is in O of h of n. Kasi ito naman yung titingnan natin. Yung h of n at saka g of n. So titingnan natin na sobrang laki ng running time as the input size grows for h of n. But then, mas okay pa si g of n. So we can then say that this is true. H of n in O of f of n. So this is also not true, because as you can see in the graph. And then h of n is in O of g of n. No, because h of n's running time is greater as the input size grows compared to g of n. Okay? So if we arrange in the following in the increasing order, O of n squared, O of 2 raised to n, O of 1, O of n log n, O of n cubed, and O of n and O of n log n. So what would be the answer? So it would be the constant, which is O of 1, and then followed by O of log n. So logarithmic, and then followed by the linear, which is O of n, and then O of n log n. So log linear na function, followed by the quadratic, which is O of n squared, followed by O of n cubed, which is the cubic, and then O of 2 raised to n, which is the exponential. Okay?